Hello. Today I am presenting the paper Locket, Robust Feature Locking Technique for Language Models. So the motivation of this work is that we notice that today's generative AI model service providers use this tiered subscription scheme where they offer black box access to different models to the customers based on their subscription tiers. So if you're a free client, you get access to only basic models. If you're a paying client, you get access to more advanced models. But this scheme is reportedly not very profitable, as you can see here. But on the other hand, what is actually more profitable is a scheme called Pay to Unlock, where we use this feature locking technique to lock a specific set of premium features for the clients. So the clients only pay for features they actually need, which are then unlocked for them. So this scheme is actually widely used across the software industry, including mobile apps, games, software products, cloud platforms, and some premium services. This scheme is actually potentially more profitable. So we want to ask the question, can we enable pay to unlock scheme for AI models as well? To do that, we need to develop a feature locking technique for language models. So depending on the client's authorized features, feature locking technique will lock unauthorized features and unlock authorized features. So for example, if coding, math, and summarization are premium features, they will be locked by default. And if the client tries to ask the model to solve a math problem, they will get a refusal response. But translation is a feature that is unlocked for the client. Then if the client is asking the model to translate something, they will actually get a valid response. So keep in mind that all of these feature separations are done within the same model. We're not keeping multiple versions of the same model. So there are several requirements for an ideal feature locking technique. First is we want it to be effective in terms of locking unauthorized features. I want it to be utility preserving so that it preserves the utility of unlocked features with and without this feature locking technique being applied. We want it to be robust against evasion attacks. We want it to be scalable so that we can support multiple features in multiple clients. So the system model is simple. The client has black box access to the model, and it is potentially adversarial, meaning that the client might perform evasion attacks to try to access unauthorized features. So for example, they can perform naive jailbreaks, they can do non-adaptive jailbreaks, they can do adaptive jailbreaks, or they can do credential sharing. To prevent these from happening, there are several storming solutions we can take. For example, we can use system prompt to refuse queries. We can use unlearning. We can use LM routers. We can just use a simple detector or classifier to identify unauthorized features. But all of these have different drawbacks, and they do not meet all the requirements. So among all of these strawman solutions, there's one that is more promising, which is called password locking, which basically enables the client to access specific features if they can provide the correct password to the model by appending that password to their prompt. So password locking functions similar to a backdoor where the LM is fine-tuned to response given a correct password, which is sort of like a backdoor trigger. But this is also limited in scalability, robustness, and utility. So all of these strawman solutions do not meet the requirements we set out to achieve. So to design a better feature locking technique, we need to avoid the drawbacks. For example, one of the drawbacks of password locking is full fine-tuning. And we find that full fine-tuning for password locking degrades utility, robustness, and scalability. So to achieve better feature locking, we need to avoid full fine-tuning and improve utility and robustness by separating access control and authorization from the model, and improve the scalability by using LoRa adapters to lock features. So instead of training one feature to lock a specific feature combination, we can train multiple LoRa adapters, each locking one feature, so that we can avoid maintaining exponential number of different versions of the same model. So recall the system model for feature locking techniques. On top of this, we add this access control module separate from the model, which determines the allowed set of features for a client, and then we selectively attach adapters to lock unauthorized features. So this is the overview of Locket, and each adapter is refusal trained to lock one feature per adapter. So there are several challenges in designing Locket. First challenge is how to ensure effectiveness. Second challenge is how do we maintain utility for unlocked features? How do we ensure robustness? And how do we make sure that when we're merging multiple adapters to lock multiple features, we're not compromising utility? To address the first challenge, we will perform simple refusal training using SFT. So we will construct this dataset consisting of prompts with unauthorized features, and they correspond to a refusal output. To preserve utility, we will collect a dataset consisting of generic text from the internet, and we will train with the scale diversity penalty so that we'll make sure the policy doesn't drift too much from its normal behavior. So to ensure robustness, we will perform adversarial training. To do that, we will first perform actual jailbreak attacks against the refusal trained model, and then we'll collect the adversarial prompts and construct this preference dataset that map prompts to chosen responses. The chosen responses are refusal outputs because we want to make sure that unauthorized access to unauthorized features are properly refused. To enforce this preference and make sure that we generalize to unseen attacks, we will leverage latent adversarial training, which basically adds adversarial perturbations to the model's latent activations. And under this perturbation, we train the model to move towards the chosen response and move away from the rejected response. So the first step of doing that is to optimize per sample perturbation. And then the second step is to optimize robustness under this perturbation. So to do that, we'll minimize this our robust loss function. To jointly optimize for utility and robustness, we will construct this final loss function, FLoTE, which is basically L robust plus L utility. The fourth challenge is merging adapters. So we found that when we're trying to merge multiple adapters to lock multiple features, we are actually faced with this challenge of over refusal. What happens is when you want to, for example, lock math and code, it will result in the model refusing to answer summarization requests, even if the summarization adapter is not attached. This is called over refusal. To address that, we basically want to ensure that merged adapters shouldn't be stronger than the strongest single locking adapter. To do that, I will design a technique called spectral norm capping, which basically scales a merged adapter back down if the spectral norm is greater than the threshold, which we set to be the maximum norm over all the adapters. For experiments, we use 4 domain-specific datasets corresponding to premium features: math, SQL, text summarization, and general knowledge, MLU. The results basically show that our merging technique is more utility preserving. Our feature locking technique is more effective, more utility preserving, more robust, and more scalable. So with this feature locking technique, we can apply it to many other areas. For example, A/B testing. So in software, we have this process called feature flagging or stage throwout, where basically we want to gradually expose features to clients. But we cannot do that currently with LLMs. But with our feature locking technique, we can actually achieve this without keeping separate model versions. And then we can also apply feature locking technique to alignment and counter moderation. So for example, we can lock age restricted features by default and only unlock for verified users. And additionally, we can achieve better regulatory compliance using our technique. For example, we can keep sensitive features like medical diagnosis locked until regulatory compliance has passed, for example, HIPAA. So in summary, in this paper, we take a system security approach to providing security and privacy for AI models. We propose a feature locking technique that can enable the pay-to-unlock scheme for large language models, which can help service providers improve profitability. And Locket is the first technique to satisfy all the requirements for an ideal feature locking technique. Thank you.